Hello student, in previous video we have studied the cumulative distribution function of a univariate discrete random variable, properties of cumulative distribution function, median and mode of the probability distribution. Now in this lecture I am going to explain the mathematical expectation of discrete random variable x. The definition of mathematical expectation of a discrete random variable x is: let capital X be a discrete random variable taking values x1, x2, xi, xn with probabilities p1, p2, pi, pn respectively. Then the expectation of a random variable x is denoted by E of x and defined as follows. Expected value of x is equal to x1 into p1 plus x2 into p2 plus so on plus xi into pi plus dash dash plus xn into pn. Now this can be written as in the form of summation. Expected value of x is equal to summation of xi into pi summation over I running from 1 to n. This is the definition of mathematical expectation of a discrete random variable. Then expected value of x, expectation of x is equal to arithmetic mean of x, that is expected value of x is equal to x bar. Now to see this, we consider the following frequency distribution. This is the variable x takes values x1, x2, dash 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 xi and xn with corresponding frequencies are f1, f2, fi, fn. Then by definition of arithmetic mean of x is equal to x bar, which is equal to summation of xi into fi summation over I running from 1 to n divided by summation of fi. Therefore x bar is equal to x1 into f1 upon capital N plus x2 into f2 upon capital N plus dash 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 plus xi into fi divided by capital N plus dash 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 plus xn into fn divided by capital N, where capital N is equal to total frequency, that is capital N is equal to summation of fi. Therefore x bar is equal to f1 upon capital N into x1 plus f2 upon capital N into x2 plus fi upon capital N into xi plus dash 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 plus fn upon capital N into xn. Then f1 upon capital N is the relative frequency, and we replace this relative frequency by probability. Now this can be written as, therefore x bar is equal to p1 into x1 plus p2 into x2 plus dash 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 plus pi into xi plus, that is last term is pn into xn. That is p1 is equal to f1 upon capital N, and this f1 upon capital N is the relative frequency of x1. Then p2 is equal to f2 upon capital N, pi is equal to fi upon capital N, and pn is equal to fn upon capital N. Now this can be written as x bar is equal to summation of pi into xi summation over I running from 1 to n. Hence expected value of x is equal to the arithmetic mean of x. Okay, that is the mean of the frequency distribution is equal to the mean of the probability distribution. Okay, then if random variable takes countably infinite number of values, in that case the expected value of x is well defined if the series summation of mod of xi into pi is less than infinity. That is, the series is absolutely convergent. See, if this is the random variable, if random variable takes countably, x takes countably infinite values, then expected value of x is well defined if series summation of mod of xi into pi summation over I running from 1 to infinity is less than infinity. That is, this series is absolutely convergent, then the expected value of x is exist. Then otherwise we say that the expectation of x does not exist if the random variable takes countably infinite number of values. Then sometimes expectation of x x may not be a possible values of random variable x. To see this, we consider a probability distribution of random variable x. We have a probability distribution, that is, this is capital X, this capital X takes values 1, 2, 3, 4, 5, 6 with corresponding probabilities are 1 by 6, 1 by 6, 1 by 6, 1 by 6, 1 by 6 and 1 by 6. Now the expectation of x of the given probability distribution is expected value of x is equal to summation of x into p of x summation over x. This is the definition of expectation. Now for the given probability distribution, expected value of x can be computed as 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. Now we take 1 by 6 as a common and write remaining term in bracket. 1 by 6 is common, then in the bracket 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is equal to 21 upon 6, that is the value of the expected value of x is equal to 21 upon 6, which is this value is the not possible values of the random variable x. The possible values of the random variable x are 1, 2, 3, 4, 5, 6, but expected value of x is equal to 21 upon 6. Hence, the sometimes our expectation of x may not be a possible value of random variable x. Now we see one example on this mathematical expectation of a discrete random variable. We have given a probability distribution of random variable x, and that probability distribution is xi takes values 1, 3, 5, 6, and their corresponding probabilities are p of xi 0.1, 0.2, 0.4 and 0.3. For this probability distribution, we have to find out the expected value. By definition of expectation, expected value of x is equal to summation of xi into pi summation over I running from 1 to n, which is equal to 1 into 0.1 plus 3 into 0.2 plus 5 into 0.4 plus 6 into 0.3. Again, expected value of x is equal to, this is 0.1 plus 0.6 plus 2.0 plus 1.8. Therefore, the expectation of x is equal to 4.5. The expected value of x is equal to 4.5, and here also the 4.5 is not a possible value of random variable x. Okay, now we see the expectation of a function of a random variable x. That is, expectation of a function of random variable x is defined as expectation of a function of random variable x. Suppose y equal to g of x. This is the function of random variable x. Therefore, y is also random variable with same probability distribution of random variable x. Using this property, we can define expectation of a function of random variable x as expected value of y is equal to expectation of g of x, which is equal to summation of g of xi into pi summation over I running from 1 to n. This is the expectation of a function of random variable x. Now we see one example on this. The probability distribution of random variable x is, the random variable x takes values 0, 1, 2 with probabilities 0.2, 0.4 and 0.4. Then let y is equal to 2x plus 3, and we have to find out the expected value of y. Now we first find out the possible values of random variable y. The possible values of random variable y are: substitute x equal to 0. The first value of random variable x is 3, and substitute x equal to 1. The second possible value of random variable y is 5. Then put x equal to 2. Then we have possible value of random variable y is 7. These are the possible values of random variable y. Then their corresponding probabilities are 0.2, 0.4 and 0.4. These are the probabilities. These probabilities are same as the probabilities of random variable x. There is only change in values of the random variable y and random variable x, and the probabilities are same. Now the expected value of random variable y is equal to summation of y into p of y summation over y, which is equal to 3 into 0.2 plus 5 into 0.4 plus 7 into 0.4, which is equal to 0.6 plus 2.0 plus 2.8. This is the expected value of the random variable y. Okay, now we see some theorems on the mathematical expectation. The first theorem is theorems on expectation. theorems on expectation. First theorem is expected value of C is equal to C, where C is constant. That is, expectation of constant is constant itself. That is, expected value of constant, expected value of constant is constant itself, is constant itself. Now proof of this theorem is, suppose xi comma pi, I takes values 1, 2, so on up to n, is a probability distribution of random variable x, is a probability distribution of random variable x. Okay, then let g of x is equal to c, a constant. C is the constant. Okay, then expected value of g of x is equal to expectation of c, which is equal to summation of c into p of x, summation over x. C is the constant, take out of summation sign, c into summation of p of x, summation over x, which is equal to c. Since summation of p of x, summation over x is equal to 1, that is, total probability is equal to 1. Hence, the expectation of constant is constant itself. That is, expected value of g of x is equal to c. This is the first theorem on expectation. Then second theorem on expectation. Theorem number 2. Theorem 2. Effect of change of origin and scale on expectation. The first case is expected value of x plus b equal to expected value of x plus b. Then second case is expectation of a into x is equal to a into expected value of x. And third case is expected value of a into x plus b is equal to a into expected value of x plus b. Now, proof of this theorem is, Let first case, let g of x is equal to x plus b. Therefore expected value of g of x is equal to summation of g of xi into p of xi summation over I running from 1 to n. Then here g of x is equal to x plus b, summation of x plus b into p of xi summation over I running from 1 to n. Okay, now this can be written as summation of xi into p of xi summation over I running from 1 to n plus b into summation of p of xi summation over I running from 1 to n. Here b is the constant, therefore b is taken out of summation sign. This is equal to expected value of x plus b, expectation of g of x is equal to expected value of x plus b, since summation of p of xi is equal to 1. Therefore expectation of x plus b is equal to expectation of x plus b. This is the proof of the first case. Now we see proof of the second case, that is expectation of ax is equal to a into expected value of x. Second case, expected value of a into x is equal to a into expected value of x. Let g of x is equal to a into x, therefore expected value of g of x is equal to summation of g of xi into p of xi summation over I running from 1 to n, which is equal to summation of a into xi into p of xi summation over I running from 1 to n. A is the constant, take out of summation sign, then which is equal to a into summation of xi into p of xi summation over I running from 1 to n, and the summation of xi into p of xi is equal to the expected value of x, which is equal to a into expectation of x, that is expected value of g of x is equal to a into expectation of x, g of x is equal to a into x. Now proof of the third case, expectation of a into x plus b is equal to a into expectation of x plus b. Let g of x is equal to a into x plus b. Therefore expected value of g of x is equal to summation of g of xi into p of xi summation over I running from 1 to n. Now substitute the value of g of x here, which is equal to summation of a into xi plus b into p of xi summation over I running from 1 to n. Now this can be simplified as follows: summation of a into xi into p of xi summation over I running from 1 to n plus summation of b into p of xi summation over I running from 1 to n, which is equal to, here a is constant and also b is constant, therefore we take out of summation sign. A into summation of xi into p of xi summation over I running from 1 to n plus b into summation of p of xi summation over I running from 1 to n, which is equal to a into expected value of x plus b. This is the expectation of g of x. G of x is equal to ax plus b, which is equal to a into expected value of x plus b, since summation of p of xi summation over I running from 1 to n, which is equal to 1, that is total probability is equal to 1, hence the proof of the theorem. Thank you.